All right, so first thing we're going to do is go around and get class totals for brown, yellow, orange, green, blue, red. You'll want to add these to your page. If you wrote down your individual counts on those lines, that's perfectly fine. We'll just put the class total underneath that so that you have your total and the class total. I'm going to go around and collect everybody's browns. I need at least 2 other people with a calculator out that can double check me, because if I put a number in wrong, we need to know. All right, so I went ahead and did this too. I had 5 brown. I'm just going to kind of move down the rows until we get everybody. Anthony, 9. 9. And Morgan? 9.
5.
How many? 5. 11. Lady?
7.
13.
13. Estrella? Brown? 10.
5.
5.
10.
10. 14. B? 6.
4.
4.
6.
6. Maya?
7.
7.
8.
8. And
4.
4. I got 142.
Yep.
Okay. So let's write down our total for brown then. 142. All right, reset the calculators. Let's do this again with yellow now. I had 9. Anthony? 10. Olivia? 11. Morgan? 16. Elijah? 12. Lacey? 12. Lainey? 12. Jude? 11. Estrella? 6. You said 10? 6. Brandon? How many yellows? 4. 4. B? 6. 9.
14.
14. Maya? 11. Lucy? 15. And Maya?
14.
14. What do we get?
Was that yellow or orange?
Yes, yellow.
15.
Oh, you got 15? And you said 14, right? You had said 14?
Yeah, I said 14 is 15.
Okay, so add 1 more to that. I got 189 when I added that 1 more. Okay. 189 for yellow. Now let's do orange. I had a lot of orange. I had 15 orange. Anthony? 14. 16. Morgan? 9. 11. You said 14. Lainey? 15. Jude? 11. Estrella?
8.
8. Anu? 8.
13.
13. 20. B? 12. Ben for orange?
16.
16.
Yes.
Awesome. Logan?
13.
13. Maya?
18.
18. Lucy?
13.
13. And Maya?
14.
14. I got 240?
Yep.
Awesome. Halfway there. All right, green next. I had 19 green. Anthony? 8. 14. Morgan? 11. 15. Lucy, or Lacey? 16. Lady? 16? Yeah. Okay. Jude? 10. 16. 13.
18.
18. Brandon? 15. 15. B?
16.
16. Ben? 14. Logan?
13.
13. Maya?
16.
16. Lucy? 15. And Maya?
14.
14. 259?
Yep.
Awesome. All right, next class, blue. I had 14 blue. Anthony? 20. 9. Morgan? 11. You said 14?
13.
13. 10. Jude? 8. Estrella? 10. 9.
16.
16. 15. B.
14.
14. Ben? 10. Logan?
18.
18. Maya?
18.
18. Lucy?
12.
12. And Maya?
9.
9. 2:30?
Yep.
Awesome. And last but not least, let's do red. I only had 5 red. 16. 5. Morgan? 5. 11. 6. 6. 8. Estrella, how many red?
10.
10. 10.
13.
13. 14. B.
10.
10.
7.
7. Logan?
Also 7.
Also 7. Maya?
12.
You said 12? Lucy?
11.
11. And Maya?
9.
9. 165? Awesome. All right, this was an entire party-size bag of M&Ms. Let's figure out how many M&Ms there were in the package. So we're going to add these 6 values together to get our total. So 142 plus 189 plus 240 plus 259 plus 230 plus 165. Somebody else go first. What'd you get? 1,225 is also what I got. Nice. Okay, so the whole reason we did this, if you've taken the time to look up at the little box, the company, Mars, that makes milk chocolate M&Ms claims that they produce them with the following distribution, that 13% of the M&Ms are brown, 14% are yellow, 20% are orange, 16% are green, 24% are blue, and 13% are red. I want to know whether or not that's true. So we are going to do a statistical analysis of this. I want to write down hypotheses for this significance test. What should our null hypothesis be? Not necessarily, because that's just the total number of M&Ms in the bag. Remember, we want to know whether or not this distribution. Everything is as they say. So the distribution is as they claim. What would our alternative hypothesis be? That it's not, that it's different than that. Absolutely. All right, so I'm going to put my numbers back in here. So the claimed distribution, the probability of blue would be 13%. Probability of yellow would be 14%. Probability of orange would be 20%. Probability of green would be 16. Probability of blue would be 24. And probability of red would be 0.13. So the claimed distribution of M&M color is true. The claimed distribution of M&M color is not true, would be our 2 hypotheses. So let's suppose that the claimed distribution is correct. If they're correct, how many of each color would you expect to get in the sample that we had? Remember, we had a total of 1,224 M&Ms. How many of that 25, not 24. How many of that 1,225 would we expect to be brown? 159.25. How did you get that? Probability times the total. Absolutely. 159.25. I can do that better. There we go. So you're going to take the number of M&Ms in our bag, which was 1225, times the probability of each of these colors. I want you guys to finish this out for yellow, orange, green, blue, and red. So find the expected number of each of these M&Ms that we would have expected to get in our sample. And I can go back to the page where we had the breakdown. All right. Check your values against mine. How closely does our distribution match what was expected? Somewhat. Which one's the biggest surprise? The green. We expected 196, but how many did we actually have? How much? 259, so that's quite a bit larger than what we expected. All right, so what I want to do now is for each of these, we're going to write down our observed amounts, the expected amounts, then we're going to subtract. We're going to square. Why do you think we square this?
Get rid of negatives.
Get rid of negatives, make sure it's a positive number. And then we're going to divide by the expected amount. So subtract, square, divide by expected. I want you guys to do that for brown, yellow, orange, green, blue, and red. I'm going to give us about, let's take about 5 minutes. If you're done in less than 5 minutes, we'll roll forward, but I'll leave us 5 minutes to do that. So I want you, let's take it up to like 2 decimal places on anything that has decimals.
Why don't we just do the absolute value instead of?
So there is a statistical analysis where they do the absolute value. I remember reading at one point why that's not the preferred. I don't remember off the top of my head right now, but I can look that up.
I don't know if it's because we always do the.
Yeah, I don't remember off the top of my head what the exact reasoning was.
And you said 2 decimal places?
Yeah, take it out to 2 decimal places. That will be pretty safe then. Almost done. Hopefully you guys are finishing up as well. All right, good grief. We are going to add up all the numbers in this last column. The observed minus expected squared divided by expected. That will be our test statistic. What'd you guys get when you added up observed minus expected squared divided by expected? I got 38.15 as well. Oops. All right. Is this fit to a normal curve? Do you think this is a z distribution? you think it's a T distribution? I'm curious. This is what we call a chi-squared distribution. Chi-squared distribution. Let me flip over here. Chi-squared is equal to the sum of the observed minus expected squared divided by the expected. If you guys have your formula sheets with you, we're going to be on the very back side. This is our chi-squared table. Does anybody need one of these formula sheets? Does anybody else need a formula sheet? Anybody else need one? Ben? Do you need one? Fine. There we go. And Maya. There you are. Okay, so if you look at the very, very back, please let me know if you need one if you can't find yours. What do you notice down the left-hand column? What's it got down the left-hand column? Degrees of freedom. Degrees of freedom. So the degrees of freedom is always going to be the number of categories that we have minus 1. How many categories did we have?
6.
6. So how many degrees of freedom do we have? 5. Degrees of freedom equals number of categories minus 1. So we had 6 categories minus 1. Our degrees of freedom would be 5. So what would you guys expect? Wait, hold on. We're going to stop here. At 5 degrees of freedom on your page, we're going to read across here, and we're going to try to find the number that is the closest to what our test statistic is. So our test statistic was what again? 38.15. What's the biggest this thing goes? 22.11. So our probability is less than 0.0005. 5 degrees of freedom. We are less than 0.0005. We got that from table C. There is a way to do this on your calculator. I will show you guys how to do a chi-squared on your calculator. You can also always use table C, like we just did here. What value would you expect to get for this test statistic if our sample was really close to what was expected? What kind of test statistic do you think we would have? I'm just talking about overall, not necessarily on the table. What would you expect that test statistic to be if what we had observed, what you guys counted out, was really close to what was claimed?
Way lower.
Way lower. It should be a small number, something close to 0 if it closely matched, right? Why?
Because there's not a lot of difference. So the observed minus expected is going to be really small. Then you're going to divide it and make it even smaller.
Yes. The observed minus expected would be a very small number because those two numbers would be super close together, so the difference is very small. You square it, but then you divide it, making it even smaller. And then you add them all up. Well, you're going to have something for your test statistic. It would be really close to 0 because the observed minus expected would be close to 0. What value would you get for the test statistic if the sample was far away from what was expected?
Big number.
A big number. Something large. Observed and expected values would be farther apart. I want to look at the numbers that we added up to get our test statistic. Did all of these values over here contribute equally to our test statistic? Which ones did the most? Blue and green. Which one between those two was the biggest? Green, with blue being a very close second compared to the other 4 colors. If it hadn't been for the blue and the green, do you think our probability would have been so small? No. What do you think a really small probability like this means?
It's insanely rare for this to happen.
If what?
If the null is true.
If the null is true, if the claimed distribution is true, what we just saw in here would be an exceptionally rare occurrence. I just bought a random bag of M&Ms at Kroger. Do you think that that random bag of M&Ms is probably a reasonable random sample? Probably. I don't think they probably counted out special just for this bag and be like, we're going to mess with that stats class, right?
Universe has a bit to
So would we reject or fail to reject? We would reject, which means we would claim what then? We have convincing evidence that it has that same implication, but that's not how I would word it. But that is the same general meaning. We would have convincing evidence that what? We would have convincing evidence. Our alternative hypothesis is that the claimed distribution isn't true. It doesn't mean that I have any idea what the actual distribution is. All I'm doing is saying that you claimed the distribution was this, and I found convincing evidence to say, no, it's not. This is called a chi-squared test for goodness of fit. Goodness of fit. I want to see how closely the actual observed values fit what you claimed to be true. Did you need me to go back? I'm sorry. I'm back. Let's go ahead and flip it over on the back side of this, though. How do you think doing a test like this would work in class if we had like 17 categories? It's going to take a hot minute to run this test, right? So our hypotheses for a goodness of fit test, null is always going to be that the claimed distribution of whatever it is true. The company claimed this, we're going to assume that they're telling the truth. Our alternative hypothesis will be that it is not true, and that's what we're looking for evidence of. Expected counts is n times p, whatever the probability is. Our test statistic, you have to do the sum, that's what that sigma means, of all the observed minus expected squared divided by expected. A very large chi-squared, so now it's not a z statistic, it's not a t statistic, it's a chi-squared statistic, which looks like a big script X. Chi-squared, very large, more convincing evidence for the alternative hypothesis. Degrees of freedom, we say it's k minus 1 instead of n minus 1. Our n was 1225. K is how many categories we had. So it's the number of categories minus 1. And then to find our p-value, you're either going to look on table C, like we did, find your degrees of freedom, find the thing that is closest to the test statistic that we had, or you can put it in your calculator. You do second vars, Yeah, second VARs, and then there's a chi-squared CDF, lower bound, upper bound, degrees of freedom. Yes.
What would lower bound and upper bound be?
Give me just a second to look at this. If you guys look at your chi-squared distribution, is that symmetric?
No.
No. Which probability are we wanting here? Like, look at the picture. What's it showing? It's showing a greater than, right? So with a very large test statistic, with a very large chi-squared, I want to know what's the probability of that or more extreme. Because we squared things, we're not going to have any negatives. It's not possible to have negatives. That's why this isn't a symmetric looking graph here. So my lower bound would be my chi-squared test statistic. Your upper bound is going to be exceptionally large because we've shaded off to the right forever. And then your degrees of freedom. So test statistic, large value, degrees of freedom. I want to go ahead and try the check your understanding. Let's go ahead and do this one together. Are births equally likely on the days of the week, across the days of the week? What would my hypotheses be? That they're all equal, or that they're distributed equally. Births are equally likely across the days of the week. What would my alternative hypothesis be? They are not. How would we calculate the expected count for each of these possible outcomes? Why? Other than the fact that it's down there. How do we come up with that?
You add the 7, the n times p.
N times p. So we're going to add all of these together to get n. And if the probabilities are equally likely, what's the chance somebody was born on Sunday?
Same as they were born on Wednesday.
And so what would that be? You can give it to me as a fraction or a decimal. 1/7, right? If it's equally likely to be born on a Sunday or a Wednesday or a Friday, you have a 1/7 probability of being born on any of those given days. So if you add all those up, and it does tell me up above 150 births. So I did 150 times 1/7. I got 21.4. I did write this down at the bottom because that's a lot of math. It's a lot of arithmetic specifically.
Just gonna be calculus lower sequences.
There is a way to use the lists in your calculator to simplify the process of finding the test statistic. I don't have time to show you guys today, but I'm happy to show you how to make use of the lists in the calculator so you don't have to do every single piece by hand for calculating your test statistic. Is anybody not done with part B yet? Getting part B down? All right, I'm going to bump part C higher up on the screen. And because of time, I'm going to go ahead and spoil and show our test statistic. Comes out to be 13.631. How many degrees of freedom should we be using? 6 degrees of freedom. We have 7 categories, 7 days of the week, minus 1. So I want you to grab table C. We're going to go to 6 degrees of freedom, so right here. We have a test statistic of 13.631. Is that contained somewhere on here?
Yeah.
Yes. It's in between which ones? So 0.05 and 0.025, somewhere in between 0.05 and 0.025 is where our test statistic falls, as far as the probabilities. Do you guys see that on there? So it's not necessarily an interval. The calculator will give you a chi-squared value, and we can calculate our p-value. Sorry, we'll calculate our p-value from that. If you're using table C, we can just say that it fell in between these two probabilities. If you use the calculator, I got 0.034, which is in between 0.025 and 0.05. What conclusion would we make? Would we reject or fail to reject with a p-value in between 0.025 and 0.05? Reject. I mean, unless they give us a different alpha value, but they didn't give us an alpha, so we assume what? We assume 0.05. So we would reject the null. Assuming the null is true, my calculator gave me a specific p-value. There's a 0.034 probability of getting a chi-squared of 13.631 or larger purely by chance. Because 0.034 is less than 0.05, we reject the null and have convincing evidence that births are not equally distributed across days of the week. Which day of the week was the most different from what was expected? Sunday. And looking at the raw value, 11 births on a Sunday, do you think the Sunday births are more likely or less likely? Less likely. We had 11 out of an expected 21.4. Most of my chi-squared came from this proportionally. What'd you say? We're going to do more on this on Monday, practicing with goodness of fit again, but yes.
Right.
Yep. Tuesday we will have a Zoom meeting. Your homework's going to be due on Wednesday. It would normally be due on Tuesday, but I don't see you guys on Tuesday. So Tuesday's a Zoom meeting. It's remote learning, yeah. So you guys will need to log into the Zoom. Assuming we get done on Monday with everything that we need to cover, Tuesday will be homework help. You have to come so you get counted present, and then I'll be there to help you with homework. If we don't get done with everything on Monday, we'll finish up the tail end of what we didn't get finished with, and then it would be time to work on your homework after that. All right? One of the papers that you guys picked up on the way in the door is this table right here. This gives our schedule up through the AP exam. Obviously, if something weird happens, it might need to change, but this is our working schedule. The test over Chapter 12 is a little bit weird. It actually has 2 different units in it. 2 different big ideas that we need to cover. The chi-squared stuff is what our test is going to be over, and that's going to be a week from next Wednesday. So it's like a week and a half away. After that test, we will cover the last piece, which is Unit 9, and we will finish that right before you take the AP mock exam so that you guys have been exposed to absolutely everything that's in the curriculum before you go take that mock exam. After the mock, we will begin reviewing for the exam itself in earnest. All right? Do you guys have any questions? Have a great one, everybody. I'll see you guys on Monday.